A tsunami can cross an entire ocean in hours, yet in the middle of the sea, you wouldn't even feel it. How is that possible? Here are the physics of how tsunamis travel thousands of miles. The process begins when a massive tectonic event, like the 2004 Indian Ocean earthquake, causes a sudden rupture in the seafloor. This shift instantly displaces a gigantic volume of water, setting the entire ocean in motion. To see why tsunamis are so powerful, we have to look at where their energy lives. While wind waves only disturb the near-surface layer, a tsunami moves through the entire water column. Because the ocean averages 2.3 miles deep, moving this colossal deep-to-surface mass generates kinetic energy far exceeding the most violent storms. This massive injection of energy creates a wave that races across the globe. Yet, because that energy is distributed through miles of depth, it remains invisible to anyone floating directly above it. As the tsunami moves away from the epicenter, it functions as a wave of flowing energy. In these deep waters, the energy moves through the water molecules without significantly displacing the surface. Because the wave is moving through a medium over 2 miles deep, it travels at speeds between 500 and 600 miles per hour, matching the cruising speed of a commercial jet. You can picture this wave as a freight train moving at jet speed. Its wavelength, the distance between its peaks, can stretch up to 600 miles. But in the open ocean, the height of those peaks is often less than a meter. Because these waves are so long, it can take up to an hour for a single wave to pass a fixed point. This is known as the wave period. This extreme wavelength explains the paradox of the invisible wave. A boat on the surface simply rides a gentle, hour-long rise and fall, unaware of the energy racing through the water below. If we can't see the wave from a ship, how do we know it's barreling toward a coast? Scientists use a bottom-up detection system. DART bottom pressure recorders sit on the ocean floor, monitoring the weight of water above them. These sensors are sensitive enough to detect a pressure change caused by a sea level rise of 1 millimeter. Tsunami centers also use a top-down approach. The SWAT satellite scans the ocean from space, measuring sea surface height with extreme precision. These satellites look for the tsunami's fingerprint, a series of short-wavelength dispersive waves that trail behind the main energy column. By combining microscopic pressure changes at the seafloor with these surface fingerprints from space, scientists can track the phantom wave long before it reaches a shoreline. The wave's stealth disappears as it reaches the continental shelf. In the shallow waters near the coast, the physics of the wave undergo a violent transformation. As ocean depth decreases, the wave's front hits the brakes. Shoaling slows the leading edge from 600 down to 30 miles per hour. The back slams into this slow front. This traffic jam compresses the wavelength, forcing kinetic energy upward, raising the water level. Because the wave is hundreds of miles long, it never reaches the steepness required to curl and break like a normal beach wave. It arrives as a fast-rising, relentless flood. The danger of a tsunami is found in its continuous volume. With hundreds of miles of ocean pushing inland behind the initial surge, the water continues to rise and flow for several minutes, inundating everything in its path. The final impact on land is highly variable. It depends on local factors like the friction of the sea bottom and the specific shape of the shoreline. To understand these risks, scientists use computer modeling, like the Tsunami N2 system, to simulate how these local variables will affect the wave in real time. These line charts compare surface elevation across different scenarios. They show that if a tsunami strikes during high tide, the astronomical water level can double the peak wave height and significantly increase the distance the water travels inland. This amplified energy can flatten entire neighborhoods, leaving only the most reinforced structures standing amid the debris. Next time you hear about a distant earthquake, you'll understand the invisible monster wave racing across the ocean toward shore.